Bismillah ar-Rahman ar-Rahim. Now we'll start section 4.3, which is mainly what? Linear combinations and independence of vectors. We did that before, but we did it in 4.1 for R2 and R3. Now we'll talk about it for Rn. It's the same idea, almost the same idea, but now we will work with Rn, not R2, R3. So what is the definition of linear combination? We say a vector W is a linear combination of these vectors, k vectors, provided that there exist scalars, C1, C2, up to Ck. So W is written in this way, which is almost the same definition like what we did before, but now we have k vectors. Yeah, before sometimes we have 2 vectors, 3 vectors. Now we extend it to k vectors. Okay. Now determine whether the vector is a linear combination or not. How to check that? Easily. We say, can I find C1, C2? So that W is a linear combination of those. So can I have W equals C1 V1 plus C2 V2? That means, can I have this equals C1 times V1, which is 1 minus 2 minus 1, plus C2, which is 3 minus 5 and 4. So I have this equation, C1 plus 3C2 minus 2C1 minus 5C2 minus C1 plus 4C2. So can I have these 3 equations, C1 plus 3C2 equals to 2, minus 2C1 minus 5C2 equals to minus 6, minus C1 plus 4C2 equals 3. Can we find C1, C2, satisfying all of these 3 equations? That's mainly what we're looking for. What we're looking for in this problem. Now the question is not only related to that, how to solve this equation. Yeah, we can solve it in many ways. We can solve it by Gauss elimination. We can solve it like equations and just we'll try to find the unknowns. All of these things we can do. So let me, let me deal with it. One idea which I can do. I will try to, this is 1, 2, 3. Either I move it to Gauss elimination or I can take 1 plus 3. You will get what? 1 plus 3. You will get C1 minus C1 gone. I have 7C2 equals to 5. So C2 equals 5 over 7. Okay. Now, be careful. I plug it in 1. Okay. I add C1 gone. I have 7C2 is equal to 5. 1 plus 3. So now substitute in 1, for example. I have C2 plus 6, not C2, C1, I mean. I substitute C2 5 over 7 plus 15 over 7 equals 2. So C1 is what? 2 minus 15 over 7, which is what? Minus 1 over 7. Correct? 2 is 14 over 7, so it's minus 1 over 7. Okay, but now I want this C1 and this C2 satisfy all of these 3 equations. Actually, I work only with the first and the third. Will that satisfy the second or not? Let us check. Check. I have what? 2 over 7 minus 25 over 7. Correct? Yeah. That give me what? minus 23 over 7, which is not equal to minus 6. So this does not satisfy this condition. Doesn't satisfy the three equations. I'm looking for C1 and C2, which satisfy all the three equations. Now, if you look at it, it seems to me that it will not satisfy this equation. So it means, can we write W as a linear combination of these? No. The answer is no. Yeah, so we cannot find C1 and C2 satisfying 1, 2, and 3, all the three equations. So it means W cannot be written as a linear combination. Let me do the same one with the Gaussian elimination. Let me do the same problem just to show you what will happen if I use the Gaussian elimination. So I have the equations. C1 plus 3C2 is equal to 2. Okay. And the other equation, minus 2C1 minus 5C2 equals to minus 6 minus C1 plus 4C2 equals to 3. Okay, I will transfer it into Gaussian elimination. I have 1, 3. Then I have right-hand side. Minus 2, minus 5, minus 6. Minus 1, 4, 3. Then I will use Gaussian elimination. Multiply to R1 plus R2. And R1 plus R3. To see what will happen. What I will have. 1, 3. This is 2. Okay. Now by 2, this will be 0. 2 times 6, 2 times 3 is 6 minus 5, that will be 1. 2 times 2, 4 minus 6, that will be minus 2. Okay. Now multiply by 1. By 1 and add it will be 0. By 1 and add it, that will be 7. By 1 and add it, that will be 5. Okay. Now we need to get rid of this. So multiply minus 7 R2 plus R3, which means what? 1, 3, 2, 0, 1, minus 2. Now this will be 0. Multiply by minus 7 and add, that will be 0. By minus 7 and add, that will be 19. So now these three equations are what? Are C1 plus 3C2 equals 1. C2 equals minus 2. And what I have here, 0 equals 19. There's a problem here. It means we cannot solve these three equations. There is no solution. So 0 cannot be 19 for these three equations. So we cannot write W as a linear combination, where we cannot find C1, C2 of what they call it, V1 and V2. So now if we do Gauss elimination, we'll get something like this, which is, it means there's no solution. Determine whether the vector is a linear combination of this or not. Let us see. Let me do it right away with the Gauss elimination. I have W will be C1 V1 plus C2 V2 plus C3 V3. That means we have what? The system. Let me write it. Minus 7, 7, 11 equals C1, 1, 2, 1 plus C2 minus 4 minus 1, 2 plus C3 minus 3, 1, 3. Okay, so we have what? We have 1 minus 4 minus 3. This is minus 7. This is the first equation. Give me this. Second equation, I have 2 minus 1, 1, and gave me 7. Okay. 1, 2, 3, 11. So the question is there, can we find C1, C2, and C3 satisfying this relation? Let us see. Gauss elimination, which is just a way to solve the equations. Try to find C1, C2, and C3. So multiply the first equation by minus 2 and add it to the second row. Multiply the first row by minus and add it to the third row. Multiply by 1 minus 2 and add, that will be 0. That will be 7. That will be 7. Multiply by minus 2 and add, that will be 21. Now multiply by minus 1 and add, that will be 0. Multiply by minus 1 and add, that will be 6. Multiply by minus 1 and add, that will be 6 also. Multiply by minus 1 and add, that will be 18. So now I can divide the second row by minus 1 over 7 by 7 and multiply or divide the third row by 1 over, or multiply by 1 over 6 or divide by 6. It's the same idea. Minus 4, minus 3, minus 7, 0, 1, 1, 3, 0, 1, 1, 3. Now I will multiply the second row by minus 1 and add it to the third row. I have what? Minus 7. That will be 0, 1, 1, 3. Here I have 0, 0, 0, 0. So the three equations becomes what? C1 minus 4C2 minus 3C3 equals to minus 7. Here I have what? C2 plus C3 equals 3. 0 equals 0, which it's okay. But now we have only two equations and three unknowns. So we can solve for using the second one. I have C2 is 3 minus C3. And using the first equation, I have C1 is what? Minus 7 plus 4C2 plus 3C3. That will be minus 7 plus what? 4C2 multiplied by 4 here. Let me do the calculation. Plus 12 minus 4C3 plus 3C3. So that gives me 5 minus C3. So now we have what? That means we have infinitely many solutions. We have infinitely many solutions. Infinitely many solutions. That means we can have C1 and C2 and C3 by just choosing C3. Let C3 equals 1. What you will get? C2 will be 2. And C1 will be what? 4. So this is one solution. So it means we can write W. That means we can write W as a linear combination of, what is it? V1, V2, V3. Actually, you have another solution. If I let C3, for example, minus 2. Minus 2. C1 will be what? C2. You can find C1, C2. No problem. C2 will be just multiply -2. C2 will be 5. And C1 will be 7. That means what? If I use this, that means W is C1, which is 4V1. I'm using C1 is 4 plus 2V2 plus V3, which is easily can check. Now, if multiply 4 here, it will be 4 minus 8, which is minus 4 minus 3. That give me -7. Now multiply 4 here. I'm getting 8 minus 2, which give me 6 plus 1, which is 7, which is this. The last one, multiply by 4. This is 4. 2 times 2, this is 4. So it's 8 plus 1 times 3, 3, which is 11. So it's correct. Also, there is another way to write W, since like if I'm using C3 equal -2, it will be what? 7 V1 plus 5 V2 minus 2 V3. This is another way to write it. You can check it. Also, this is the correct one. So this is what we mean by a linear combination. So sometimes we cannot find C1 and C2 satisfying all the three equations. So it means we cannot write W as a linear combination of these two vectors. Here, here we can find C1 and C2. We have infinitely many solutions. Actually, we can have many C1s, C's. Huh? So we can solve it at least. So W can be written as a linear combination of these two vectors, of these three vectors in this case. Now, if we have vectors in a subspace, we say this word span. What they mean by the span? We say collection of vectors span the vector space if what? If every vector in V is a linear combination of these k vectors. In another word, these vectors generate all of the space. Any vector in the space can be written a linear combination of these k vectors. So this is what they mean by span, the word span. Okay. Also, they call it spanning sets. V1, we call it span set. If what? We say it's a span of V1, V2. It means it's the linear combination of these vectors. So any vector in that space will be generated by those vectors. We say span of S, or we say S spans W, or W is spanned by S. All of this has the same meaning. It has the same meaning. Okay, we have this theorem, which says what? If I have V1 vectors, then the set W of all linear combinations is a subspace. If I make the set all linear combinations of V1, V2 up to Vk, then this is a subspace. This set will be a subspace. Huh? So W is what? W will be all linear combinations Ck, such that V1 up to Vk belongs to K. This will be W. Okay. This set will be a subspace. Now they define what's the meaning of linear dependence. We did it before for R2, R3. Now we expand it for any R, for any Rn. It said linear dependent if this relation C1 V1 plus C2 V2 plus CK Vk, if it is equal to 0, it has only this trivial solution. That can happen only if C1 equals C2 equals CK equals 0. Okay. It means if we can find C1 up to ck, at least one of them non-zero, it means they are linearly dependent. They are linearly dependent. Also, we have this information, a set of vectors is linearly independent if and only if each finite subset is linearly independent. Not only that, if a set is linearly independent, then every subset is also linearly independent. And if a set has a linearly independent subset, then it's linearly dependent. Okay. Now let me check. Yeah, let me remind you how to check these vectors are dependent or independent. We need to solve this system. C1 V1 plus C2 V2 plus C3 V3 equal. We have three vectors. Note these are in R4. Huh? If I can find C's, not all zeros, it means they are linearly dependent. If all the C's are zeros, it means they are linearly independent. Okay, we need to solve the system. So the system, let me change it. Yeah, if you want to make it right, the system C1 1 2 2 1 plus C2 2 3 4 1 plus C3 3 8 7 5. That is equal to 0 0 0 0. So what is the system? C1 plus 2C2 plus 3C3 equal to 0. 2C1 plus 3C2 plus 8C3 is equal to 0. What else? 2C1 plus 4C2 plus 7C3 is equal to 0. C1 plus C2 plus 5C3 is equal to 0. Let me change it into matrices, and then I will do Gauss elimination. I'll try to do it quickly. 1, 2, 3. I have 0 here. 2, 3, 8, 0. 2, 4, 7, 0. 1, 1, 5, 0. So multiply by minus 2 R1 plus R2 and minus 2 R1 plus R3 and minus R1 plus R4. We have 4 now. Okay, let me do the calculation. Actually, later we'll tell you a way to decide quickly, but now let me do the calculation. Multiply minus 2 and add, that will be 0. Minus 2 and add, that will be minus 1. Minus 2 and add, that give me 2. Minus 2 and add, that will be 0. Minus 2 and add, that will be 0. Minus 2 and add, that will be 0. Minus 2 and add, that will be 1. Minus 2, that will be 0. The last one. Minus 1 and add, that will be 0. Minus 1 and add, that will be minus 1. Minus 1 and add, that will be 2. That will be 0. Okay. I can multiply the second row and the third and the second row by minus 1. Yeah. And then, yeah. To save place. So let me do it. That means this is 1 and this is minus 2. Okay. Okay. That give me what? Now, after that, I'll multiply the second row by minus 1 and add it to the fourth row. Because this is already 0. No need to worry. I have 1, 2, 3, 0. 0, 1 minus 2, 0. This is 0, 0, 1, 0. Multiply by, okay. Multiply by 1. Multiply by 1. Huh? Sorry. Yeah. Multiply by 1 and add, that will be 0. Multiply by 1 and add, that will be 0 too. And this would be 0. Okay. So now if you look at the equations becomes what? C1 plus 2C2 plus 3C3 equal to 0. I have C2 minus 2C3 equal to 0. C3 equal to 0. That if C3 equals to 0, put it here. C2 will be 0. Put those two here. I have C1 equals 0. It means this is the only solution. C1 equals C2 equals C3 equals 0. That means what? V1, V2, V3 are linearly independent. This is the definition, where I have all the C's are zeros. Okay, another example. I need to determine whether these collection of vectors are linearly dependent or independent. Let us see. I have 4 vectors in R3. I have 4 vectors in R3. So I need to check C1, V1, plus C2, V2, plus C3, V3, plus C4, V4 is equal to 0. I have C1 to write just the equation. I'm doing it in details. Yeah, C3. Okay, so what are the equations? I have 2C1 plus 5C2 plus 3C3 is equal to 0. C1 minus 2C2. Oh, don't forget here. I have plus 2C4 is equal to 0. C1 minus 2C2 plus 8C3 plus 7C4 is equal to 0. I'm doing it in detail. Actually, you can write it as a Gauss, as the matrices right away. But yeah, I'm doing it in details here. 3C1 plus 4C2 minus 6C3 minus 4C4 is equal to 0. So I need to solve this system. Actually, 2, 5, 3, 2, zeros. 1 minus 2, 8, 7, 0. 3, 4, minus 6, minus 4, 0. To avoid having fractions, I will interchange R2 with R1 so that I have 1. So it will be easy to do the calculation. That give me which matrix? 1 minus 2, 8, 7. This is 0. 2, 5, 3, 2, 0. 3, 4, minus 6, minus 4, 0. Okay. That will give me what? Now, minus 2, R1 plus R2, and minus 3, R1 plus R3. You'll get what? 1 minus 2, 8, 7, zeros. Multiplied by minus 2, this will be 0. Multiply by minus 2 and add, that will be 9. Multiply by minus 2 and add, it's minus what? Minus 16 plus 3, that will be minus 13. What strange numbers? Minus 2 and add, minus 14 plus 2, that will be minus 12. Multiply by minus 3 and add, that will be 0. By minus 3 and add, that will be 10. By minus 3, minus 24, minus 24, minus 6, that will be minus 30. By minus 3 and add, that will be minus 25. Yeah. Is it? By minus 3 and add. Okay. Minus 3 and add minus 25. 0, 0. Okay. Okay. It is very complicated. Yeah. Is it correct? 1 minus 2. Is it 1? Oh, I interchange it. Okay. 1 minus 2, 8, 7. Okay. 2, 5, 3, 2. 2, 5, 3, 2. 3, 4, minus 6. minus 4, okay. Minus 2, that would be 9. Minus 2, 16 plus 3. Yeah. Minus 16 plus 3 minus 13. Minus 2, minus 14 plus 2 minus 12. Yeah, I think this is correct. Just make it complicated now. Minus 24, minus 30, minus 25. Yeah, I can divide by, yeah. Yeah, I think we need to deal with fractions. Let me simplify this one. 1 over 5 R3. Yeah. 0, 9. And I will interchange R2 with R3. Just I want to make the calculation easier. Let me divide by 10. Just I have fractions, okay. So I have 1 minus 3, and this one is what? Yeah, minus 2.5, which is minus 5. I divide by 10, 25 over 10 minus 5 over 2. This is 0. This is 0, 9, minus 13, minus 12, 0. Now multiply by minus 9 and add it. Minus 9, try to solve it. Minus 9, R2 plus R3. You understand what I did? I multiply by 1 over, you need to find ways to solve this. I multiply by 1 over 10. Then I interchange R2 with R3. Okay. So I have what? This is 1 minus 2, 8, 7, 0, 0, 1, minus 3, minus 5 over 2, 0. Now multiply by minus 9 and add, that will be 0, 0. By minus 9 and add 27 minus 13, that is 14. By minus 9, yeah, fraction here. It's 45 over 2, huh? 45 over 2 minus 12, which is 45 minus 24 over 2. That will be 21 over 2. So that give me 21 over 2. 21 over 2. This is it. Okay. So what I will do, I will change it now into equations. Change the equations. So I have C1 minus 2C2 plus 8C3 plus 7C4 is equal to 0. C2 minus 3C3 minus 5 over 2 C4 is equal to 0. You can solve it in different ways, but this is the way I think it is better. Plus 21 over 2, this is C3, C4 is equal to 0. So from here, I can say no, C4 will be what? Yeah, minus 14 times 2 over 21. Yeah, C3. Or let me write C3 in terms of C4, maybe better. Yeah, you can write this or that, it's okay. So C3 will be minus 21 over 2 times 1 over 14. C4. So this is 2. Yeah, and this is minus 3. So I have minus 3 over 4 C4. Okay. Let me give me a little bit of space. Okay. Yeah. Yeah, I'm doing it in a lengthy way, but this is just to understand what's going on. So C3 equal minus 3 over 4 C4. Okay. And now from here, C2 equal 3 C3. Okay. Plus 5 over 2 C4. Which is what? Minus 9 over 4 C4 plus over 2 C1. I'll write everything in terms of C4. So it means we can find values. And that means what? This is will be 1/4. Yeah. 1/4 C4. Yeah. Is it? Yeah. Is it with the -9? Multiply by -3, that will be -9/4. Okay. Now, what else? We have the first equation, C1 equal to C2 minus 8C3 minus 7C4, which is what? I have C2 is this, and C3 is this. Plug it there to find C1. I have what? Half C4 minus 8, so it's plus 24/4, which is 12, which is 6. C4 minus 7C4. That give me what? Half minus 1. صح? Half minus 1, which is minus half C. So now I let C4 is equal to what? Yeah, I think I will make it 4. That will make it better. So I have C1 will be -2, and C2 equal 1, and C3 will be -3. So it means W can be written, or that means what we call them? V1, since I can't find C's, satisfying this relation. So I can say no, V1, V2, V3, V4 are linearly dependent. Actually, we have this conclusion. If I have k vectors in Rn, k vectors with k greater than n, then the vectors are linearly dependent. If I have the number of vectors is more than the Rn, the n in Rn, which is we call it later the dimension, then these vectors are linearly dependent. For example, this case, wait a minute. Yeah, we have how many vectors? We have 4 vectors in R3. Right away, without doing any of these things, any of these calculations, right away, I can conclude, these vectors are linearly dependent. This is the first things. If I have the number of vectors is more than the dimension of Rn, more than n, which is in Rn, we call it the dimension in the next section. Number of vectors is greater than n, right away, these vectors are what? Linearly dependent. The next case, if they are the same. If they are the same, then we need to do what? Remember this determinant, we can check it, we can do it. So we say n vectors, n and Rn, n vectors in Rn are independent, and only if this matrix has non-zero determinant. I think we did that in the, so I need to check the determinant of A not equal to 0 to say in V1 are linearly independent. If the determinant is equal to 0, that means they are linearly dependent. The last things, if the number of vectors is less than n, so the number of vector is less than n, so we'll do what? So we have this matrix, having them as its column vectors. Then the vectors are linearly independent if and only if some k by k submatrix of A has non-zero determinant. I'll try to take k by k submatrix and check if it has non-zero determinant, then the vectors are linearly independent. If not, I mean, we cannot check all of these submatrices. I will try to do it in the next recording, but this is yeah. The idea is what I will take K by K submatrix and check it has non-zero determinant or not. Yeah. So if he yeah. So I think I will stop here and I will come back to this conclusion. So just to make it short, these two are easy. 1 and 2 are easy to do. 3 we'll talk about it more in the next recording. But the idea, if the number of vectors is more than the dimension of Rn, which is, then we say right away the vectors are linearly independent. If they are the same, then I will do it through the determinant. And then the last one, which is if they are less, number of vectors is less than n, then there is a way through taking submatrix, K by K submatrix, because we cannot find the determinant if we don't have a square matrix. So we'll take square matrix K by K. If I can have a submatrix which has a non-zero determinant, then we say they are linearly independent. If we cannot, we cannot check all of these submatrices, so we cannot conclude easily. We can go back to the main definition, which is this one. The vector is independent if I can find C's. Okay, we'll stop here, and I will have another video later. Well, we have time, so why not? I try to do at least some problems, and then which concluding this. Okay, now let me do this since we have time. It's still, and usually I want my videos to be around 1 hour, so I think I will do that. Now determine this. How many vectors we have? We have 3 vectors. Well, you know what? I will go back to the previous examples which we did. Okay. Now, how many vectors do we have here? We have 3 vectors in R4. So the number of vectors is less than n. So we need to do it through this submatrix. I'll leave it. This one I want you to notice. I have how many vectors? I have 4 vectors in R3. Right away, they are linearly dependent. And this is what he said here. If the number of vectors is less than n, then right away these vectors are linearly dependent. No need to do any of these calculations. No need to do all of this calculation. Right away you can conclude this. No need to do all of this and make it in 2 pages. No need to do all of these things. Okay. Okay. Let me do these ones. I have 4 vectors in R. I have 3 vectors in R4. 3 vectors in R4. So I have which case? I have this one, third case. Okay. What you will do, I will write it as a vector. I have 1, 1, minus 1, 1, 2, 1, 1, 1, 3, 1, 4, 1. Okay. The question is, can I take submatrix? Look, submatrix related to K. K, which is the number of vectors, huh? K is the number of vectors. So I need 3 by 3 submatrix, where the determinant submatrix, let me call it S. The determinant of S not equal to 0. If that happened, then right away, V1, V2, V3 are linearly independent. Okay. Yeah, you can have many cases, but I'll take, I need square matrix. I'll take this square matrix, check 1, 1, 1, minus 1, 1, 4. So I'll try to do these things. Let me do it quickly. Multiply by -1 and add, that will be 0. -1 and add, that will be -1. -1 and add, that will be -2. 1 and add, that will be 0. 1 and add, that will be 3. 1 and add, that will be 7. So I have what? -7 plus 6, which is -1, which is not equal to 0. So I have a submatrix of 3 by 3. 3 by 3, because I'm working with 3 by 3. Where the determinant right away, V1, V2, V3 are linearly independent. The first two cases are very clear. Just okay. Now another example. I need to check they are linearly independent or not. Okay. So I have 3, 0, 1, 2. The same case. I have 3 vectors in R4. So the number of vectors is less. I have 3 vectors in R4. The same idea. Okay. 1, -1, 0, 1, 1, 2, 1, 0. Okay. This is what happened. So now I need to check. Let me take this submatrix. See what will happen. Okay. I'll take 3, 1, 1, 0, -1, 2, 1, 0, 1. Okay. I can deal with the second column. Multiply by 1 and add. That give me, you need to find the determinant your way. 1, 1. I multiply by 1 and add. That will be 3. By 1 and add, that make it 0. By 1 and add, that will be 3. 1, 0, 1. So I'll do the expansion with the second column. So I have what? Plus minus, that will be -1. Cancel this with this. 3, 3, 1, 1. I'm getting 0. Can I conclude that they are linearly dependent? No, we cannot conclude that. I can conclude if I take all the possible submatrices, which is very complicated. So what I will do, I will go back to the previous definition, which is trying to find the C's, solving the system. So I need to find the system. I cannot conclude. To conclude, I need to check all submatrices, because the theorem is saying what? If the vector, if there is some one submatrix has non-zero determinant. So you need to check all the submatrices. This one also combine the third with the first with the third and the fourth. So you need to do all of these ones. I mean here, you need to do this one, check. You can do the first with the third and the fourth, which is a little bit complicated. So we cannot conclude, no conclusion. So what I will do, solve it. We solve for the C's. Let me do the our way. Now I have, let me do it quickly. 3, 1, 1, okay. 0, -1, 2, 1, 0, 1, 0, 1, 0. I'm solving the system. 0, 0, 0, 0. Okay. So I can interchange the third with the fourth, with the first, to see ones. That will be easier for calculation. 0, 0, -1, 2, 0, 3, 1, 1, 0, 0, 1, 0, 0. So now multiply -3R1 plus R3. I'm getting what? 1, 0, 1, 0, 0, -1, 2, 0. Multiply -3 and add, that will be 0. minus 3 and add, that will be minus 2. Am I right? No, what's this? Minus 3, multiply minus 3, and add it with this one, that will be 1. Minus 3 times 0 is 0. Minus 3 times 1, that will be minus 2. This is 0. Now, the last one, it is 0, 1, 0, 0. Okay. Now, what I will do, I will do the same trick like what we did before. Multiply by minus R2. That will be 1. That will be minus 2. And see what will happen. Oh, I did the mistake. Three, 0, 3, 1, 1, 0, minus 1, 2, 1, 0, 1, 2, 1, 0. This is not 0. Sorry, this is 2. Change the color. Sorry, I made a mistake. This is 2. So I need to, I need to multiply minus what I did. This is 2. Now I need to multiply, before I do this, I need to multiply the first row by minus 2 R1 and add it to the fourth row. That will be 0. That will be 1. Minus 2. That will be minus 2. Okay. Now I do this minus sign, so I have what? 1, 0, 1, 0, 0, minus 2, 0, 0, 1, minus 2, 0, 0, 1, minus 2, 0. Now multiply the second by minus R, second row by minus and add it to the third row. Second row by minus and add it to the fourth row. You have what? 0, 0, 1, minus 2, 0, 0, 0, 0, 0, 0, 0, 0, 0. So I have what? I have C1 plus C3 equals 0, and C2 minus 2C3 equal to 0. From here, I'm getting C2 equal to C3. From here, I'm getting C1 equal minus C3. So I let C3 is equal to 1. So I have C2 is equal to 2 and C1 equal minus 1. So we have solutions. We actually have infinitely many solutions. So the vectors are linearly dependent. The vectors are linearly